Stoichiometry is the use of ratios to compare one substance to another in a chemical reaction. So if we are looking at a very simple reaction, which is actually just a recipe, okay, let's pretend like it's really this easy to make pizza, even though I know it's not. Our coefficients here are 1, 5, 2, make one pizza. So 1 pizza crust, 5 ounces of sauce, 2 cups of cheese makes a very simple pizza. The ratio here is 1 to 5. So for every 1 crust, we need 5 ounces. For every 5 ounces of sauce, the ratio to cheese is 5 to 2, etc., etc. So with stoichiometry, you can compare reactants to products. So for example, there's 2 cups of cheese to every 1 pizza. Okay, you can compare products to reactants. Every 1 pizza needs 5 ounces of sauce. You can compare reactants to each other. So 1 crust needs 5 ounces, whatever. It doesn't matter as long as you're using the coefficients that are in front of the substances. So if you're solving a question like this, we always start with the number that's in the problem. So 6 cheese. Okay, if we use the ratio of cheese to pizza, okay, there's 2 cups of cheese for every 1 pizza. So we are going to set this up. 1 pizza. Okay, we want the unit that we're looking for to be on top so that it doesn't cancel out, and you want the unit you're getting rid of to go at the bottom so that it will cancel out. Okay, there's 2 cheese. So cheese is going to cancel out. So 6 times 1 divided by 2 means with 6 cups of cheese you can make 3 pizzas. Okay, and this is assuming that you have plenty of crust, plenty of ounces of sauce. We can also compare, like if we know we have a certain amount of cheese, then we can figure out how much sauce would we need to go with that. So we're going to go back to our 6 cheese. For every 6 cups, we need 5 ounces of sauce, and that is 2 cups of cheese. Okay, so again, cheese is going to cancel out. That's our goal. So 6 times 5 is 30, divided by 2 means we need 15 ounces of sauce. That's not how you spell sauce, silly Miss Doss. Anyway, okay, so if we're actually using a real chemical reaction, our coefficients here are 2, an invisible 1, and a 3. So the questions are pretty much always set up the same way. They usually begin by asking you what you're looking for or by stating what you're looking for, and then they end with what you're beginning with. So we know that we have 6 moles of NH3. The ratio of ammonia to hydrogen is 2 to 3. So we're going to multiply by 3 hydrogens and divide by 2 ammonias. So what we're saying here is for every 2 ammonias that we use up, there's going to be 3 hydrogens that replace it. And this is going to leave us with 9 moles of H2. The reason why the unit is mole is because mole did not cancel out. The only thing that canceled out was the NH3. So essentially we did 6 moles times 3 divided by 2, which is why mole is still the unit for our answer. Okay, one more example of mole to mole. So we have aluminum compared to magnesium. So this is a single replacement reaction. If we know that we want to create 12 moles of aluminum, for every 2 aluminums that is produced, we have to use 3 magnesiums. So we're going to put 3 magnesiums here and 2 aluminums. And that means that we need 18 moles of magnesium. Okay, again, mole did not cancel out. It was just the aluminum that we got rid of and replaced it with magnesium. So these questions get harder when you have grams because grams cannot be directly compared to each other. And we've talked about this, you know, you can have 1 atom of carbon and 1 atom of oxygen. That's a 1-to-1 ratio, but the masses of them are not the same because of protons and neutrons. So if you have grams in the question, you have to switch it to moles because moles is really talking about how many atoms or how many molecules of a substance you have. So in this case, we're starting with 37.2 grams of carbon dioxide, so we're not going to be able to do anything with that. Okay? Eventually, we know this plant is consuming a certain amount of carbon dioxide. We want to figure out how much glucose it's making. Eventually, we'll be able to switch it from one substance to another, but we have to start with turning this into moles. So we're going to divide by the mass of carbon dioxide, which is 44.01. So our ultimate goal here, if you have grams, turn it into moles first, and then you can get started. And that gives us 0.845 moles of carbon dioxide. Okay, so next step. Now that we have moles of carbon dioxide, we can do the actual stoichiometry. So for every 6 carbon dioxides that are consumed by a plant, there's going to be 1 glucose molecule that can be made from that. So we're going to take the moles of carbon dioxide we just figured out, multiply by 1, divide by 6. So the unit is not going to change because there's no unit in the ratio here. What's changing is we're getting rid of carbon dioxide and we're turning this into moles of glucose. And the answer for that so far is going to be 0.141 moles of glucose. Okay, so we have successfully turned grams of carbon dioxide into moles, then we use stoichiometry to turn carbon dioxide into glucose, and now we have a value for glucose. The problem is this is not a measure. I'm sorry, my iPad just froze for a second, so I have no idea what the last thing I said was, so I'm going to repeat myself a little bit. The problem is that this is not a measurable value for glucose. Okay, it's not you can't measure moles. We don't have a piece of equipment that can do that. So we really have a third step here where we need to figure out what is the mass of glucose that is equal to 0.141 moles of glucose. And the way we do that is we need to say that 1 mole of glucose weighs 180.18 grams. Okay, and the reason why we're doing that this way is because now we want moles to cancel out. So the final answer is 11.9 grams of glucose. Almost every stoichiometry problem that you do is going to be at least 3 steps because realistically in a lab scenario you're finding mass, you're not finding moles. So if you're actually answering a real question, it's going to be based on mass. You have to use moles in order to find the answer. So this one, okay, we are going to figure out how much acid do we need to neutralize this base? So again, our issue is we're starting with grams. Okay, in order to compare a base to acid, we need to get to moles. So first step is always divide by the molar mass of the substance that you have, which is 58.33. And that gives us 0.0559 moles of magnesium hydroxide. So again, we got rid of grams, but we still have magnesium hydroxide, which does not really do us that much good because what we really want is hydrochloric acid. So this is, now that we have moles, this is the step where we can do the actual stoichiometry and use the ratio to convert from magnesium hydroxide to acid. Okay, which the ratio is 2 acids for every 1 magnesium hydroxide. So now we're going to still have moles, but now we're actually getting rid of the substance itself. And that turns into 0.112 moles of hydrochloric acid. This question specifically reminds you that you should really turn this into mass. So we're going to say 1 mole of hydrochloric acid is equal to 36.46 grams. I'm doing that in my head, so I'm sorry if that's not exactly correct. And then final answer, 0.112 is 4.08 grams of hydrochloric acid. And so if you were, let's say you were setting up for a lab, if you knew that this is the value that you were starting with, you could use stoichiometry to figure out exactly how many grams of one substance you need to go get in order to neutralize the other substance. So this is a much more usable unit. And of course, since this is AP Chemistry, we can't just stop there because we did those last questions when you were in honors. We have to take it one step further. If you have kilograms of a substance, that presents a new problem, which is that moles is in regular grams, not kilograms. So we have to add another step to stoichiometry. So at the very beginning, you're starting with 25 kilograms of sulfur dioxide. The first thing we need to do is convert to grams. So we're going to divide, okay, it's times 10 to the third, so we have 25,000 grams of sulfur dioxide. And now we can pick up and do regular stoichiometry. So we have 25,000 grams of sulfur dioxide. We need it to be moles so that we can convert from one substance to another. And this leaves us with 390.2 moles of sulfur dioxide. Okay, so first step, we got rid of kilograms and got regular grams. Second step, we got rid of grams and got moles. We still have sulfur dioxide, and the question is asking us for how much acid we can make. So the ratio of acid to sulfur dioxide is 2 to 2, which basically is just 1 to 1. So there's not really any extra math here. This is just converting, or that was supposed to be SO2, excuse me. Okay, we're just getting rid of SO2 and we're converting to acid, but the number stays the same since it's a 1 to 1 ratio. So now we have moles of acid. Okay, then we need to start turning the moles of acid into usable units. So we're going to take 1 mole and multiply by the mass of sulfuric acid. So we end up with 38,274.7 grams. Okay, and this number is a little bit too big. So let's say the question had asked you that, I just cannot get 8s to work right on this stupid thing. Let's say the question had asked you to specifically say kilograms. Since this is 38,000, then we would need to do the last step, which is to convert back to kilograms. So we'll do the opposite of what we started with, and we have 38.274. There were only 2 sig figs in the original number, so we're really just going to drop all of these and say that the final answer is 38 kilograms of acid.